1950, the Navy's Military Sea Transportation Service assumed the resupply of existing weather stations and military bases in Greenland, Labrador, Alaska, and the sealing stations on the Pribilof Islands in the Bering Sea. In 1955, MSTS was called upon to sea lift equipment and supplies to support construction of Dew Line, a distant early warning radar barrier spanning the North American continent. The problems of this sea lift were many. Variable ice conditions, difficult to predict. Navigation through hundreds of miles of uncharted shoal and ice-infested waters. Offloading of cargo on primitive beaches. Training of personnel for the rigors of the Arctic. And preparing the ships for wintering in, should a return to safe water not be possible. Ice is undoubtedly the biggest problem to be faced in Arctic shipping. However, ice reconnaissance flights have helped to solve this problem and have proved invaluable, not only in advanced planning, but in the actual transit itself. There are three types of ice reconnaissance: long-range, tactical, and local reconnaissance, each playing its own role in the forecasting and reporting of ice conditions. The first of these, long-range reconnaissance, is necessary for successful operational planning. Good ice forecasting expedites routing and reduces ice damage. Navy aerographer mates identify the characteristics of ice masses and record their observations. The location and extent of pressure ridges, cracks, and leads, and the percentage of puddling, as well as the age. All features, including ice-free water, are recorded using standard symbols. However, the master or the commanding officer conning his ship through ice fields is not at the moment too concerned with the ice forecast for next week. His concern is the ice field directly ahead. How far does it extend? Which course will be the least hazardous? Tactical reconnaissance flights provide the answer to these questions through their daily flights along the shipping route. They fly in close support of the ships in transit and transmit local ice conditions directly to the ships by voice radio. The third type of ice reconnaissance deals in close operational support. Helicopters are invaluable in this respect due to their versatility. In close range observation, helicopters search out open leads and report ice conditions directly to the ships by voice radio. Due to the problems of locating a downed copter in close ice, their operational range is normally restricted to 10 miles from the parent ship. The buddy system has been employed so that one will be on hand to render immediate assistance should a casualty occur in flight. Sea ice, combined with strong currents, erratic tides, shoal water, pinnacle reefs, and unreliable charts, make navigation in these northern waters a hazardous and difficult task. Hydrographic survey units have done much to decrease the element of chance. Each summer, ships specially equipped to conduct surveys worked ahead of supply ships, sounding out safe water and recording their findings. As a result of their efforts, sounding tracks were surveyed, establishing safe shipping routes into every landing site in the eastern Arctic. In addition, over 1,700 miles of sea lanes along the Dew Line in Alaska and central Canada have been covered by reconnaissance surveys, and a safe shipping route charted. Detailed surveys were conducted in the most critical areas, and sections of the coastline were covered by triangulation. Many radar reflector towers have been erected as aids to navigation. And finally, a deep draft ship route from Shepherd Bay through Ray, Franklin, and Bellot Straits into Prince Regent Inlet and Lancaster Sound was surveyed and navigated. Underwater demolition teams, working with advanced hydrographic personnel, surveyed and prepared beaching charts of each offloading site. Sounding lines were run on triangulation fixes to determine beach gradient. Wading and swimming in line abreast, frogmen surveyed bottom conditions. When obstructions were found, demolition charges were used to remove the hazards. In areas where ice is moving, continual searches must be made for boulders. Between tides, ice has been known to move boulders weighing several tons onto the beach. Therefore, UDT personnel should remain with operating units until all offloading has been completed. Fixing the ship's position in northern waters imposes many problems not encountered in low latitudes. Climatic factors such as fog, low ceilings, and continuous daylight prevent customary celestial observations. Even during periods of good visibility, ice horizons and mirages complicate obtaining precise altitudes of the sun. The best method of navigation is to fix the ship's position relative to identifiable land masses. This is possible in most instances along the dew line. Radar is essential to safe navigation. It enables the navigator to identify charted landmarks and permits ranging on visible bearings. The abrupt, rugged coastline of Labrador, Baffin Island, and Greenland provides excellent radar targets for close navigation. However, the low sloping beaches in Fox Basin and westward to Alaska do not lend themselves well to detection. Therefore, in these areas, radar reflector towers, erected well back from the shoreline, provide positive targets for the navigator. 2 radar sets are recommended: the main set for normal use and a smaller set for close range work. Radar is the only possible method of determining the ship's position during the periods of heavy fog, which are fairly common during the summer months. Therefore, check your radar regularly to assure its proper operation. The magnetic compass is of little value due to proximity to the magnetic pole. Daily variations average 8 to 10 degrees, while 40 degrees have been noted during periods of magnetic disturbances. The gyro compass, modified for operation north of 70 degrees latitude, gives very satisfactory results. Small compass errors of 2 or 3 degrees are common, but in view of other factors, are not critical. Radio stations at radar sites permit use of radio direction finders. Low-frequency RDF sets are recommended for best results. Operating frequencies of site stations should be checked before entering the area. Charts of the area are still quite void of soundings. Consequently, the fathometer should be operated continuously while underway. A portable fathometer, calibrated to read in feet, should be carried in each ship. Installed in a workboat, it becomes a valuable instrument for searching out shoals and checking beaching sites without subjecting the ship to unnecessary dangers. Taking lead line soundings is an almost forgotten art. but necessary at times on ships not equipped with a power boat. Ships employed in Arctic operations are selected for specific purposes. The shipping routes of the eastern Arctic permit the use of deep draft vessels. In this area, Victory cargo ships carry the bulk of all dry cargo. T2 tankers are used to transport bulk petroleum. LSTs are utilized to some extent where tides and beach characteristics permit their beaching. LSDs, landing ship stock, are used in all areas of the East to transport lighterage, support equipment, and Army cargo handling personnel. LSDs also perform repair and salvage operations when necessary. In the western Arctic, deep draft vessels, such as the Task Group Command and Communication Ship, an AGC, can navigate as far north as Point Barrow. T2 tankers and LSDs are also operated this far north. East of Point Barrow, however, shallow draft vessels drawing not more than 16 feet are used exclusively. 5,000-ton Samavis, commonly referred to as knot ships, carry dry cargo and LCM lighterage. AOG tankers move the bulk petroleum products, while support equipment, troops, and bulk cargo are transported in LSTs for direct offloading onto the beach. The use of shallow draft ships is the result of experience. In 1955, Victory ships rounded Point Barrow, and because of their deep draft, were required to operate offshore in heavy pack ice. All ships received ice damage, and 2 returned under tow. In the East, heavy icebreakers escort shipping whenever ice conditions warrant, and conduct hydrographic surveys when not so engaged. In the West, the icebreakers are assigned to areas along the northern coast of Alaska, where pack ice is a continual threat to shipping. Waggles, shallow draft Coast Guard buoy tenders, reinforced for light icebreaking, assist ships operating in shallow waters where large icebreakers cannot venture. The ARS provides repair and salvage assistance east of Point Barrow in place of LSDs. Thin-skinned conventional ships are not basically designed for ice operations. However, over the years, extensive alterations have made them more suitable for this work. Ice sheathing, reinforced with double framing, protects critical waterline areas on AOGs and LSTs. Bow wrapper plates have been added to other ships. Bottom doubler plates installed on LSTs at the bow, at main and auxiliary engine rooms, and at boiler evaporator spaces provide added protection. Special ice service propellers of high tensile strength bronze alloys have proven more satisfactory than steel or stainless steel wheels. The position of LST's rudders makes them quite vulnerable to ice damage. Soft brass shear pins were installed in steering quadrant linkage arms, and with new high-strength rudder posts, structural damage to rudders has almost disappeared. Topside, pilot houses were installed and equipped with a remote radio telephone handset for tactical communications. The regular set, mounted on the bridge, is equipped with a selector switch, which permits its use from either station. Chain towing bridles should be made up and rigged, ready for instant use. Experience proved that wire cable towing bridles were not satisfactory. Each ship should be equipped to tow or be towed, for, despite hull strengthening, some casualties may be unavoidable. The number of ships which can be escorted by an icebreaker, normally 3 or 4, depends on the concentration of the ice field. A beamy ship, such as an LST or T2 tanker, should follow to keep the lead made by the breaker open. Propeller wash and stern design cause openings to close quite rapidly. So close formation, as specified by the escorting ship, is mandatory. When in close formation, accurate station keeping is a must. Use a statometer during good visibility. When visibility is poor, use radar for station keeping. Rig a cargo cluster light on the stern as a marker for ships following. Frequent course changes are often necessary to avoid hitting ice. However, if ice cannot be avoided, hit it with the stem. This will be less damaging than striking the ice with the flare of the bow. When backing down in ice, always keep the rudder amidships. A zigzag course is normal. It is easier and much safer to go around ice than through it. On turns, watch your stern as well as your heading, or a flooded compartment, or a damaged propeller may result. Ice lookouts should be stationed, particularly when maneuvering astern, to alert the bridge when ice is in the way of propellers and rudder. Sound-powered telephones provide quick and efficient communication to the bridge from lookout stations. Maneuvering through ice is not easy, but is essential to delivery of Arctic cargo. A few established bases in the east, such as Thule and Goose Bay, have limited port facilities for offloading dry cargo. In these ports, tankers drop anchor and pump their cargo to the beach through semi-permanent submerged lines. Steep rocky beaches characterize the cargo offloading sites in the eastern area and make cargo operations difficult and hazardous. There are no port facilities here, and cargo discharge becomes an over-the-beach operation. Cargo handling equipment is moved to the beach and stevedoring operations commence. LCUs and LCMs ferry cargo ashore from ships at anchor. Extreme tides, as encountered at Frobisher Bay, hamper operations, permitting cargo to be worked only during high tides. The western Arctic is characterized by low gravel beaches and negligible tides. The shallow gradient often makes it necessary for earth ramps to be constructed. LCMs and LVTs handle all cargo at some sites where conditions do not permit LST beaching. Bulk petroleum is discharged from offshore tankers through standard 4-inch hard rubber hose with neoprene floats attached. 1,500 feet of this hose in 30-foot lengths is standard allowance for these ships. Shore connection is made to pipelines leading to beach tanks. Shore pumping stations then transfer the oil to the site tank farm. The operation continues until all tanks are full. Bulk diesel is also carried as cargo in wing tanks of LSTs and in spare tanks of Samavis. Samavis generally offload into LSTs, which discharge in the same manner as tankers, offshore or directly over the beach. After completing discharge, recover the hose by hauling it aboard through the bow doors, making certain that a fair lead is maintained. LCUs and LCMs, equipped with special tanks and independent pumps, are used at some sites to assist in offloading bulk fuel when ice, weather, or distant offshore anchorages prevent direct hose connections. During all offloading operations, voice radio communications should be maintained between shore personnel, lighterage, and the ship, utilizing portable radio telephones. Radar reflectors installed on all small craft provide quick identification should fog suddenly close in. LCVPs should be octasized to minimize ice damage. This is accomplished by installing sheathing over the wooden hull. Equip at least one boat in each unit to do light salvage and repair work. Ships at anchor must keep a sharp lookout for drifting ice. Pressure of large blocks and floes has caused the loss of anchors and chains. When cargo operations are halted by ice or weather conditions, flexible stowage plans permit ships to move to another anchorage site. The short shipping season does not permit waiting out in anchorage when other sites are clear. The ever-present hazards of Arctic shipping emphasize the need for well-equipped ships and well-trained crews. Prior to departure, check all emergency equipment. Familiarize the crew with its location and exercise them in its use. For example, test electrical submersible pumps for proper operation. Rig and operate the portable peri-jet eductors. Familiarize and drill the crew in firefighting and damage control techniques. Proper use of emergency equipment is best learned through simulated casualties. Drill the crew in man overboard procedures. All hands must act quickly in such an emergency, for survival in Arctic waters is measured in minutes. Check deck watch officers out on visual signaling. Instruct the entire crew in the use of inflatable rubber life rafts. Life jackets are of little value in the extremely cold Arctic waters. Therefore, carry 50% additional life rafts or floats. Familiarize the assigned personnel with the operating characteristics of the LST and other landing craft. Practice beachings and stern-to-stern salvage drills will prepare them to assist in actual salvage operations. Conduct highline transfers during underway training. Valuable experience gained by such practice will pay off when an actual transfer problem arises. Dry docks and repair facilities are few and far between in the eastern Arctic and are non-existent in the west. Therefore, ensure that the crew is prepared and that equipment is available to make emergency repairs. A question in the minds of every man entering the Arctic is, will we be forced to winter in? To date, no MSTS ship has been inadvertently forced to spend the winter in the ice. Operation 1957 West, however, concluded with the planned wintering in of 6 ships to be used for the resupply of the central Canadian sector during the 1958 season. Although this planned venture differed in many respects from a forced wintering in, the same basic principles apply. Select a refuge site that is protected from pack ice by land masses or natural breakwaters. Current and tidal conditions should be at a minimum. Water must be of sufficient depth to avoid the ships freezing to the bottom. Fix the mooring position a sufficient distance offshore to prevent accidental grounding in the event of dragging during the winter. The first ship into the planned wintering in area carried special mooring buoys and equipment. These buoys were laid at pre-designated locations. Cement blocks anchored the buoys vertically, while reinforced folding anchors were positioned at right angles to the mooring nest. In order to plant dead men for anchoring the mooring buoys, the rock-hard permafrost had to be thawed with steam hoses and loosened with explosives. The ships then moved into the prepared mooring nest and made fast to the beaches with chains. Manila mooring line cannot be used, since its center rots rapidly when exposed to the cold. After mooring the ship, the next steps in preparing for the wintering in deal with the preservation of specific gear and equipment. Remove all topside portable fittings and equipment and stow below. Remove compasses from their binnacles and pack safely with other portable navigation equipment. Install canvas covers on all topside navigational fixtures. Including the radar antenna. Remove all running rigging and stow below decks, leaving cargo gear until last. Slack off standing rigging to relieve any stresses set up by ice pressure. Meanwhile, the engineering force must perform its wintering-in preparations. Install special diesel space heaters to assist in the lighting off stages in the spring. Seal all exposed electrical boxes against moisture. Drain the oil boxes on all winches and refill with special Arctic oil. Use the air compressor to blow out water lines and deactivate the ship's systems in the order of their importance. Break, drain, and tag all steam returns. Siphon dry all bilge and ballast manifolds. Remove all standing water in the bilges and tanks. Drain the generators and engine cooling systems and fill with antifreeze. Drain all heat exchangers and leave open to reduce rusting. Fill stern tubes and all sea chests with a special Arctic oil to replace entrapped water, thereby preventing damage from freezing. Rubber floats may be inserted and inflated in sea chests of LSTs as added protection against freezing in event of loss of oil. Transfer of perishable items ashore and evacuation of personnel are the final steps taken. The ships are now prepared to withstand a winter in the Arctic, unmanned and abandoned to the sub-zero temperatures and gale force winds, yet ready for reactivation for their next year's operation. This film has emphasized the major problems encountered during an Arctic sea lift, based upon the actual experiences of military sea transportation service ships. These problems can be overcome by advanced preparation, aerial reconnaissance, hydrographic survey, the proper outfitting and preparation of ships for Arctic operations, flexible stowage plans, training of crews, good seamanship, and eternal vigilance. Experience to date has demonstrated that military and commercial shipping can conquer the Arctic.